Now, what if we decide to work on something like a deck of cards? And we're going to work with poker because it's such a convenient tool. How many of you play poker? At least sometimes? Okay, not that many. Okay, so the way we're going to do this is we're going to say we've got 52 cards, there's nothing wild, there are no jokers, and we're just getting 5 cards. And the question is going to be, how many different hands of poker can you get? Yeah, and there are a lot of them.
Mm-hmm.
There are a lot more than 48. That's why we have to learn how to count first. But the structure is always going to be the same. We're going to use experiments, have sample points, and those are going to comprise the sample space. As a recurring example, we're going to use sort of a business situation where the two companies, Markley and Collins, can have these absolute results. Now obviously this is a simplification because these are absolute results. But by the same token as with the dice, how many different sample points can you get when you have two companies like that? And they're not tied together at the hip. Okay, so clearly that wasn't clear enough. If Markley makes 10, Collins can make 8, or Collins can make -2. If Markley makes 5, Collins can make 8, or Collins can make -2, and so on. So how many possible sample points are there? 8, right? 3 times 4. And in general, you just take the number of possible outcomes for each experiment or each layer, and you multiply them all together, which can turn into a fairly large sample space. In this case, though, only 8. You can also illustrate this with a decision tree, and we're going to be using decision trees extensively once we get to our expected value of imperfect information. But it helps you get some sort of structure. And what happens, usually, not necessarily in this case, but usually you would like to have this in some sort of time-ordered fashion, or so that decisions made down here depend on what's happened here. But in reality, these two stages may very well happen simultaneously. Okay. So in order to, like I said, count and work with a large sample space, we're going to introduce 2 tools, permutations and combinations. And, well, for some reason, this is one of the most difficult things to work with. It's one I had a tricky time understanding it. And so we're going to take this one step at a time. Imagine that you have 2 people and you want to construct a board of 2, president and secretary. There are 2 people. How many ways can you organize those 2 people? 2 ways. Everybody happy with that? All right, now add a third. How many ways can you organize a board of 2 when you have 3 people to choose from?
6 different.
And how'd you get that?
3 times 2.
Right, 3 times 2.
3
There are,
2 ways.
I'm sorry?
3 people to jobs.
3 people to choose for the first president, and then that leaves
2 people.
2 people to choose for the second position, right? So 3 times 2. Everybody see that? And actually, this is sometimes helpful, just a list. I'm just going to give you. So basically, these are the 3 names. This is the president. This is the secretary. And you've got 6 different ways of doing this. Yes? All right, what happens when we expand to 4? 4 people to choose from, you're still only using a board of 2. What's that? No?
24.
No?
40.
What's that?
34.
No? How many can you, let's pick president first. How many ways can you choose president?
4.
4. So that leaves how many choices for secretary?
Three.
3. 12.
Yeah.
There are 12 ways to choose 2. And when you care about order, when you care about who's president and who's secretary. Now, how many times, I'm sorry? You're ahead of us. So let's not go there quite yet. But you're right, if we did not care about order, did not care about titles, then we would divide by 2, because every single group of 2 is going to show up twice, yes? Okay. Now, the logic here was, you basically take the larger number and you multiply by one smaller, yes? So if we go all the way up to the number of people in this class, 21, how many ways could we pick a president and a secretary from this class?
Same. 2 all.
21 times 20.
Oh.
Is that clear to everyone? Okay.
Okay.
Now let's expand that one step further.